All right, let's talk about this processing, heating, and cooling curves and calculating the energy of a phase change. So in the first place, when do you even use these heat of fusion or heat of vaporization constants? What kinds of calculations? Um, these constants are needed when you are calculating the energy required or released during a phase change. So the equations are Q equals the heat of fusion times how many moles you're trying to melt or freeze, and Q for vaporization, for boiling or condensation. Contrast what happens to particles during a phase change or versus a temperature change. During a phase change, the distance between particles changes. In other words, their potential energy increases, they grow further apart, or decreases, they grow closer together. These happen on the flat parts of a heating cooling curve. In contrast, during a temperature change, the spacing between particles stays the same, while their kinetic energy changes. If kinetic energy increases, the particles move faster, they have a higher temperature, while the particles move slower and have a lower temperature when Ke, kinetic energy, decreases. These temperature changes can be easily pointed out by the slanted portions of a heating or cooling curve, which we're going to do an example of right here. Okay, so let's draw a cooling curve for water. It starts at 108 degrees Celsius and it cools down to minus 15 degrees Celsius. So this is temperature and this is time, and this is energy released over time as this cools. Okay, so it's going to go down, and then right around 100 degrees, it's going to plateau because that is the special temperature for water where it goes from a gas to a liquid. Then it cools down again until it hits about 0 degrees Celsius where it freezes. So it's going to plateau, and then it's going to go down again as it gets colder as a solid. So potential energy is decreasing at the plateaus here and here. And portions where the kinetic energy is decreasing are here, here, and here. The melting point, boiling point, condensation point, and freezing point. So this is the freezing / melting point, 0 degrees for water. And this is the condensation / if it were going in the opposite direction, the boiling point. And then we need to label all the states of matter. So here we've got a gas, here we've got a gas and a liquid, here we've got a liquid, here we've got a liquid and a solid, and here we've got just a solid. How much energy is required to boil 1.5 moles of liquid water at 100 degrees Celsius? Well, if we're boiling, we use the heat of vaporization formula. And so we need to look up this constant for water. So here's water, and the heat of vaporization is 40,700. So 40,700 joules per mole, and it says that we are trying to boil 1.5 moles of water. So I'm going to multiply these together. I get 61,050 joules of energy required to boil 1.5 moles of water. Okay, one more problem. How much energy must be released to freeze 100 grams of liquid iron at 1,535 degrees Celsius? Hint, the molar mass of iron is 55.85 grams per mole. Show which equation. Well, that is the heat of fusion times moles, and all of your work in units. Okay, so we've got 100 grams of iron, and we're going to need to know how many moles this is. So 1 mole of iron is equal to 55.85 grams. That's the molar mass from the periodic table. So 100 divided by 55.85, that is about 1.79 moles of iron. Okay, so that's 1.79 moles. And then we also need to know the heat of fusion for iron. So let's look up iron and the heat of fusion used for melting and freezing. It needs to release 13,800 joules per mole in order for this to freeze. So I'm going to take 1.79 times 13,800, 24,702 joules released to freeze that iron. There you go.